volume is up. All right, so we take a look at question number 1, 2, and 3. So Robert, you're first with number 1, 2, and 3. So in question number 1, electron current model flows from what side to what side of a voltage source? Flows from negative to positive, everybody, for question number 1. Question number 2, for conventional current, which way does the current flow from what side to what side of the voltage source? Robert? Positive to negative would be the answers for number 2. Number 3, what are the subatomic particles that exist within the nucleus of Bohr's model of the atom? They are what? And? In the nucleus. Protons and neutrons. You should have 2 answers there. It's not split up as 2, but there are 2 that fit in there. 1 would not be complete. Any questions on 1, 2, and 3? Okay, 4, 5, and 6. Question goes to Sarah. Number 4, what subatomic particles exist outside the nucleus?
Electrons.
Electrons for number 4. Number 5, which are positively charged?
Protons.
Protons are positively charged. Number 6, which are negatively charged?
Electrons.
Electrons are negatively charged. Any questions on 4, 5, and 6? No. Next, 7, 8, and 9 goes to AG. So for 7, which are not charged?
Neutron?
Neutrons are not charged for number 7. Number 8.
No idea.
Okay, so charges that flow in a circuit would be current, okay?
Okay.
Then current number 9.
Static?
Static electricity would be correct for number 9. Number 10. Yeah, you can do number 10. Let's finish up with number 10. With the most common method of creating static electricity, which would be what?
Friction.
Friction would be the most common one. Any questions from 6 through 10? No. 11, 12, and 13 go to, let's see, Youssef. What is defined as the pressure to move electricity?
Voltage.
Voltage. What is defined as charges in motion?
Current.
Current. And opposition to electricity flowing is? Resistance. For 11, 12, and 13, any questions? No. 14, 15, and 16 goes to Jacqueline. Can there be electricity flowing without a voltage source?
No.
No, cannot be without a voltage source. Number 15, can there be a voltage source without electricity flowing?
Yes.
Yes, there can be. The battery would be an example of it. Number 16, omega symbol represents what electrical quantity? It represents, yes, it represents ohms. It represents the physical quantity is resistance. The unit is ohms, yes. Okay, so we're looking for resistance for number 16. Any questions for 14, 15, and 16? Okay, 17, 18, 19, and 20. Let's go ahead and do all those. Robert, if voltage remains the same, current will do what if the resistance is doubled?
Increase.
If you double the resistance, like the pedals of a bicycle, Robert, you increase resistance, what's got to happen to current? It's got to go down. But not only does it go down by a specific amount? Anybody? It goes down by half, okay? Or halve, H-A-L-V-E, okay, is what we're looking for number 17. Number 18, if resistance remains the same, the current will do what if the voltage is doubled? Robert?
Increase.
It will increase, but specifically by how much? Class?
Double.
Double. If the voltage is doubled, then the current will double.
So the answer is double.
Yes, if you just say increase, it would be half a point. Okay, all right. Let's continue, spread the wealth. Sarah, number 19. If current remains the same, voltage must be what if resistance is doubled?
Increased by double.
Increased by a factor of 2 or just simply doubled. Yeah, either answer would work. And number 20, voltmeters must connect how in order to measure volts?
Be in parallel.
Must be in parallel. Any questions for number 17, 18, 19, and 20? We're done with the first page? Fast. Look how fast you guys are zipping through this final. All right. Question number 21. Let's take a look at the next page. Question number 21, 22, and 23. That will go to WG. Ammeters connect how to measure amps?
In series.
In series. Now, I did rephrase number 22, and I sent that out by Discord, could you take a look at the question as I rephrased it? Can you measure voltage with a digital multimeter by contacting a single point, yes or no? Wei Ji?
No.
No. You have to contact with a voltmeter how? 2 points. Must be 2 points, okay? Number 23, your bathroom GFCI wall outlet will trip when what happens?
Short.
When the best answer is when a ground fault is detected. It is a short, yes, but specifically a ground fault. Okay, any questions on 21 through 23? 24 through 26, that will go to ESYS. 24, what engineering prefix do we use? Milli, so lowercase m, yes? Okay, number 25, which engineering prefix do we use? Pico, so lowercase p. And number 26, what exponent should we have here?
-6.
10 to the -6 power for number 26. Any questions 24 through 26? 27 through 29, that would go to Jacqueline. So 27, what exponent for number 27? 10 to the 9th power would be correct. Good job. And number 28, can you be electrocuted in pure water? Not in pure water, no.
That's an insulator.
Yeah. Pure water is, you're safe with pure water. But how often are you going to be standing in a puddle of pure water? It ain't going to happen, all right? But just, yeah. Your regular water has minerals in it, and it's the minerals that act as electrolytes that will conduct electricity that will shock you in an instant. But pure water has no electrolytes in it, no minerals. It actually doesn't taste very good. So, I mean, some minerals are good for you. So, no, in pure water, you cannot be electrocuted, to be clear. Number 29, what is the current in a circuit with a 5 kilo ohm potentiometer adjusted to its midpoint with a 10-volt source? What did you calculate, Jacqueline?
4 milliamps.
4 milliamps. Who does not have 4 milliamps and does not understand the question?
I have
Okay.
4 amps.
Huh?
I have 4 amps.
4 amps?
Yeah.
Well, here, okay. We have a 10-volt source. Yes, everybody?
Yes.
We have a potentiometer adjusted where?
To 2.5 kilowatts.
Midpoint, which is what? 2.5 kilo, right? So if you take 10 divided by 2.5 kilo, you should have 4 milliamps.
I forgot the kilo.
Because the potentiometer is adjusted midpoint. The potentiometer is adjusted halfway. And half of 5 kilo is going to be, wow, look at these. I got to put this on pause for a moment. Ha, ha, ha. Hold on. Come here. And Sarah?
Yeah,
Okay.
I forgot the exponents.
All right, yeah, so whatever happened there, yeah, all right. And so question number 30, resistance of the, blank is the resistance of a potentiometer circuit, 15-volt source and 10 amps flowing should be 1.5 ohms, 1.5 ohms. Okay, now we have a very interesting circuit. So let me go ahead and snip this guy. Okay, everybody see my screen okay? All right, so you were asked for several characteristics regarding this. How would you start this particular exercise? Question goes to Robert. How would you start this? Because you asked for a lot of different things, so. By redrawing it, excellent. And when you go to redraw it, when you go to redraw this, how would you redraw this? What would we simplify first? What are you going to combine in your redraw?
R2 and R3.
Okay, we're going to redraw. We're going to combine R2 and R3. So we should have this circuit here. And this guy come over to here. REQ number 1. And REQ number 1 would be 35 ohms plus 40 ohms, yes? So this gives us 75 ohms over this side, is that correct? R1 over this side is 50 ohms. So now you've got 3 resistors simplified down to 2 resistors. What would be the next step? The next step is to redraw this one more time. Redraw. And in redrawing this one more time, we would end up with an R total. And R total is equal to R1 in parallel with REQ number 1, yes? So this would be 50 ohms in parallel with 75 ohms. Everybody do this calculation right now, 50 parallel to 75. And while you're doing that, let me label some points of interest here. I'm going to label this point A, label this point B. Here is A, here is B. Here is point A, and here is point B. So RT should calculate to be what value here, Sarah?
30.
30 ohms, yes? Everybody okay with that? Once you have 30 ohms, then can you calculate an IT? So IT is equal to your 75 volts, divide by your 30 ohms, and your IT, I'm going to do these a little bit out of sequence, that's all right. Wei Ji, what do you calculate for IT?
2.5 amps.
2.5 amps. So 2.5 amps, if you will, if you look at this right here, 2.5 amps is flowing out of the negative side of the source. So your 2.5 amps is your I total. What happens to this current when it hits node B? It's going to split. Part of the current's going to come up here, part of it's going to continue and come up here and go on up like so. And then the current at the top, this will wrap around and join, and then it'll come around here. So the direction of current that is drawn at the very top by the artist shows I pointing to the right. What model current is the artist showing in the schematic? Whole current, otherwise known as conventional current. What did I draw in red lines? What kind of current did I draw in red lines? Electron current. So we have 2.5 amps. Now, how does this split? Well, you can do this a couple of different ways. Let's see. Yusuf, can you suggest one way to find these currents through the first branch and the second branch? You could use current divider formula. Is there another way that you would suggest, Jacqueline?
To find the current in branch 1, you could just do 75 over 50.
Yes, you could do that. You could do Ohm's law, which I think is a little faster than current divider in this case. We could certainly use current divider and it will work for us. I would prefer working with less effort, and Ohm's law is less effort because between point A up here, here's point A, and point B down here, don't we have a 75 volt source? And isn't that entire 75 volts across this 50 ohm resistor? So your IR1 is equal to your 75 volts over your 50 ohms, and that should calculate to be 1.5 amps. Is that correct? And if you do the same on the other side happens to have an REQ that we calculated earlier over here, that was 75 ohms, yes? Well, this is also point A, this is also point B. So between point A up here and point B down here, don't we have our 75 volt source? What is 75 volts divided by 75 ohms? Yeah, your REQ number 1 is IR2 equals IR3, is that correct? And so this is equal to 1 amp. So does the math work out? If you look at this, if I have 1.5 amps coming up here, and I have 1 amp coming here, when these two meet, the 1 amp and the 1.5, do they add up to be 2.5? That's really sloppy, I'm sorry. Does that end up to be 2.5 amps going back to the source? Yay? So have we solved for all the currents in all of this? Now you have to calculate your voltages. So now take a look at question number 31. According to question number 31, it's asking you how much voltage would be measured if the red probe was connected to the bottom of R1. So here's the red probe at the bottom of R1. Imagine that as the red probe. And the black probe is said to be connected to the top of R2. And here's the top of R2, right there. So how much voltage would we read between these 2 points? Isn't the black probe the same as if it were here? Is that the same as the black probe on this corner of the circuit? Okay, right there. And the red probe where I've drawn it, isn't that the same as if, oops. Isn't that the same as if I put my red probe right here? Huh. So the red probe senses what polarity first as we pull it towards the black probe? So the voltage at, for question number 31 should read how much voltage? It should read negative 75 volts. So number 31 equals negative 75 volts. Is everybody clear on that? How about your voltage across R1? What is your VR1 for question number 32? Number 32, VR1. When you're looking at what's asked of you, R1, the voltage across R1, doesn't specify which lead goes where. So here you're only looking at 75 volts as an absolute value. And then for number 33, which is my VR2, and VR2 should work out to be 35 volts. Anybody have any questions why? You have 1 amp, you have 1 amp flowing through. You have 1 amp flowing through both of these resistors, flowing through the second branch. So 1 amp times 35 ohms will give you 35 volts. Okay, that's 1 amp times 35 ohms. That's how you get 35 volts. Okay, next question, number 34. Your RT we calculated was 30 ohms. Number 35, your IT we calculated was 2.5 amps. Number 36, the IR3 was equal to 1 amp. And number 37, the IR1 was equal to 1.5 amps. Okay, I think we solved everything there is to solve for that particular exercise, yes? Any questions on that particular guy? Nope. All right, next circuit of interest will look like this. Let me make this a little bigger so we can see it. So everybody see the circuit okay? All right, so Yusuf, how do I begin to solve this particular exercise?
Redraw it with R2 and R3 equivalent.
Okay, so I should have in my redraw from here to here, my voltage source, this guy here, and my REQ number 1. And REQ number 1 is equal to R2 parallel with R3, which is equal to 20 parallel with 30. What do you calculate REQ1 to become? Yusuf, do you happen to have that number? Everybody calculate 20 parallel with 30. 12 ohms. That's my REQ number 1. And then in the original schematic, my R1 is 38 ohms. So if my R1 is 38 ohms, my REQ is 12 ohms. What is my RT? 50 ohms. And my voltage source is given as 25 volts. So the very first thing we should have for number 38, we should have RT is equal to 50 ohms. Number 39, we should have IT is equal to what? 500 milliamps. Any questions on 500 milliamps? It's a 25 divided by 50. That's how you get that. And then number 40 is for IR1 is also 500 milliamps. because IT which flows back to the source also flows through R1. So you have 500 milliamps here, and you have 500 milliamps coming back to the source, 500 milliamps leaving the source, and you're going to need to determine how this current splits between R2 and R3 branches. We'll figure that out in a moment. Number 41. So number 41, the voltage across R1 should work out to be, class, 19 volts. Number 42 and 43, 42 equals 43, which is equal to how many volts? 6 volts. And once you realize you have 6 volts there, you could do current divider, yeah? Or you could use Ohm's law. I'd rather use Ohm's law. Again, it's faster than current divider. So 6 volts divide by 20 ohms, and then 6 volts divided by 30 ohms will get you the current. So number 44 should work out to be how many milliamps? 300 milliamps. And number 45 should work out to be 200 milliamps. Any questions on that? So far, so good? Okay. Okay, everybody see this pretty well on the screen? All right, so some of us may differ by just a few millivolts here and there, but you shouldn't be that far away from these values. So let's see, Jacqueline, help us out with here. Amplitude, you counted this as how many divisions to the peak?
2.2,
You counted this as 2.2?
sorry, 2.4.
Yeah, 2.4 divisions would be a lot closer to what we're looking for. 2.4, if you look at the one at the bottom, it might be 2.5. I might have moved this a little bit. How many people counted this as 2.4 divisions? Raise your hands. How many people counted as 2.5 divisions? Raise your hands. Okay, we're good. We're going to be within a few millivolts of each other. If you counted it as 2.4, if you counted it as 2.4 up to 2.5. So at 2.5, you're looking at 37.5 millivolt peak, yes? Okay, and if you double that, you will have 75 millivolts peak to peak. And then if we stay with those numbers and calculate RMS, you should have 26.52 millivolts RMS. And then your average is 23.87 millivolts average. Okay. Now, counting the number of divisions will be 4 divisions going horizontally for a period, yes? So one cycle from here to here is 4 divisions. So 4 times 300 microseconds is going to be 1200 microseconds, but you know that's not proper engineering notation. So what should we be writing down here? 1.2 milliseconds. Is that a lowercase s or a capital S? Oops, sorry. I'm just going on. Yeah, I'm trying to get, I just realized my Arco is not red. Now it's red. There we go. So we should have 1.2 milliseconds, yes? And if you reciprocate that, the frequency should work out to be 833.33 hertz, yes? Okay, are we good with that particular question? All right. Next. So number 47, VRMS sine wave. The answer for number 47, let's go to Robert. What do you have for number 47? Okay, so number 47 is, what is significant about VRMS? The VRMS is equal to the amount of DC voltage needed to produce same amount of power output. And so if V RMS is equal to, in this case, 85 V RMS, then 85 volts DC is needed in substitute to produce same amount of heat/power. Okay, so that's the significance of RMS. So if we have 85 volts RMS, we're going to need 85 volts of DC. Number 48, 3 capacitors in series, and then number 49, 3 capacitors in parallel. So number 48, Sarah, what do you have for them in series?
5 microfarads.
5 microfarads, and number 49?
45 microfarads.
45 microfarads. Everybody okay with how they're calculated? They work backwards compared to resistors. All right. All right. Let's take a look at, number 50 is a very interesting one. Let's go ahead and take a look at number 50. Oh, bless you, bless you. Okay. LED that requires 15 milliamps at 1.4 volts is connected to a power supply with a limiting series resistor as shown. Power supply set to 6 volts. What resistance would you specify for the limiting resistor? So the question goes to Wei Ji. How would you go about solving this? What are the facts? I think you should start with the facts. What are you given?
The supply power minus the required voltage.
So LED requires 2 things. LED is like a load on a voltage divider. What does it require? It requires 1.4 volts at 15 milliamps. So that is given. What else is given?
Voltage source.
Yeah, voltage source is equal to 6 volts. Anything else given? Okay, no other numbers are given. So where would you start this particular exercise? Start with, I would recommend, start with the schematic, because what you're given is a drawing. So if we do a schematic, let's go ahead and draw a source. We have a source, and then we have a resistor, and then we have an LED, yeah? So here's an LED, and all of this is hooked up together like so. And let's go ahead and polarize this guy. Positive, negative, negative, positive, negative, positive. And I have positive going back to the source. Okay, so far so good. And what else would be helpful in this particular exercise? Maybe it wouldn't hurt if we set up a simple V I omega for a couple of things here. Let's see how this works for us. So you happen to have a resistor, you happen to have an LED, you happen to have totals. And so if the LED, we're not concerned about this particular value. But do we have some givens that we can put on here? All right, let's go ahead. What are we given? We have a 6 volt source, yes? 6 volts. What else are you given? The LED requires 1.4 at 15. So this requires 1.4 volts at 15 milliamps. Yeah, 15 milliamps. 15 milliamps. And your task is to find this value of R up here. So, Wei Ji, you were starting to give us a solution to this. How do you approach this?
We got the voltage on the R.
Yeah, how do we find the voltage on R?
We just use the 6 volt minus the 1.4.
Okay, does everybody take a look at this carefully? Isn't it going to be the 6 volt source? Right here is my 6 volt source. 6 volts right here. Do this green. 6 volts right here. And it says we require 1.4 volts for the LED. So if I have a total of 6 volts and I require 1.4 for the LED, how do I find the voltage on the resistor? I subtract, yes? Isn't 6 minus 1.4 going to give us what we're looking for? Cool. So how much is that, Wei Ji?
4.6
4.6 apples, what?
volts.
Ah, okay, we have to speak it out. So 4.6 volts. Are we clear if we should have 4.6 volts on the resistor? Everybody clear on how we determine that? Because we got to lose some voltage across the LED. So now, does the 4.6 added to the 1.4 in fact give us the 6 volts total? We good with this? So far so good mathematically? So we have 4.6 volts here, and we have 1.4 volts here with the 6 volt source. Now do I have enough information to determine my R value? How do I determine this value of R?
Or as constant in the series circuit.
Ah, yes, because this is a series circuit, so that must mean my current is the same. And wasn't current given? You didn't even have to calculate that, right? Current is 15 milliamps. So now do I have enough information to be able to calculate the ohms? So R is equal to V over I, which is equal to 4.6 volts over 15 milliamps. So the R in this case calculates to be, Wei Ji?
306.67
306.67
ohms.
ohms. Is everybody good with that number? Everybody understands why? Cool. All right. A number of people had asked questions regarding number 51 and 52. Were they the same? And I said in Discord that no, 51 and 52 are not the same. That 51 asks you to do a calculation of, oh dear, asks for a calculation of time constant, yes, tau. So for number 51, everybody should have 1 second, yes? So number 52, everybody should have how many seconds? 5 seconds. Any questions on that? We good? Okay. Number 53, you have a cap coded at 473. If you have a cap that's coded as 473, so cap equals number 473. What do you do with that to determine its capacitance value? That would be determined as 47 followed by 3 zeros followed by picofarads. So when you key this into your calculator, oh, did I lose the screen again? Sorry. We'll just get that screen back in just a moment. Hang in there. It's got to turn red. Okay, it's back to red. All right. So that is equal to, and it did show up. All right. When you key this into the calculator, it's 47,000 EXP negative, and pico is what power of 10? Negative 12. So when you key that into your calculator and you hit your big equal sign, all of a sudden your calculator will show you 47 nanofarads, yes? And although I would accept 47 nanofarads, we know 47 nanofarads is not a standard unit for capacitors, right? We really ought to go to microfarads. And so if we go to microfarads, it works out to be 0.047 microfarads. Is that correct?
Wasn't technically either 0.047 microfarads or 447,000 picofarads accurate for standard?
Yes, either one of these is appropriate because the picofarads and microfarads are the standard increments, and also 1 farad. Those are the standard increments for capacitors. Given a choice between these two, the industry does go to microfarads, goes to the decimal. That's a smaller number of digits. I don't know if that's the reason why, but that happens to be the standard is for it to go to microfarads as opposed to that 47,000 picofarads. Okay, that being said, recalculate one time constant, still using the 10K ohm resistor. Well, this is a domino effect because if you don't have a proper interpretation of 473, then the next question, number 54, you're going to have some problems with, right? So number 54, if you do this correctly, number 54 should work out to be what? 470 microseconds. is equal to tau. And so number 55 should work out to be 2.35 milliseconds, because it would be your 470 microseconds times 5 in order to give us this number here. Are we good with that so far?
So number 54 wanted us to change the capacitor.
In the above circuit to 470 to 0.047 microfarads. Yeah. To the coded value of 473. And so,
Didn't say that, that's why I asked that question.
okay, that's why I'm available via Discord if you run into any issues along the way. And the same thing is true too, during a final exam, when we do this with each other in class next week. You certainly can raise your hand, call me over, and I will slap you on the head and say, you should know that. Or I might gently say, nudge you and say, well, you know, you might try Ohm's law or current divider, or give you something helpful. I'd rather give you the carrot than give you the stick. Come on. What's up with this barcode? Be nice to me.